So now we're going to talk a little bit more in depth about one way of learning representations. And we're going to focus on Word2Vec, which is a very popular algorithm in natural language processing for finding representations. And at this point, I would like to clarify something. Even though Word2Vec is typically used in deep learning applications, it itself really is not a deep learning algorithm, as we'll see in a little bit. It's actually a very shallow representation, but it creates representations that are very useful in deep learning applications. So, it itself is not deep learning, but it is useful because of many of the developments that we have in deep learning. And the reason that it came about is that while you can learn these representations using something that is honest-to-goodness deep learning, the elegance of the algorithm allows you to learn these representations on massive amounts of data, which is one of the things necessary for deep learning to be successful. So what we'll talk about today is Word2Vec from a high-level perspective, and then we'll look at how Word2Vec works before going into a more mathematical treatment of how you actually update the parameters when learning Word2Vec from data. Although Word2Vec is typically talked about as a generic algorithm, when people talk about Word2Vec, they typically really mean one specific piece of code that's available on GitHub and that has been very widely used. And from a very high level, what Word2Vec does is it takes a bunch of text, computes some statistics on that text, and then generates representations for words found in the original text. And the output of Word2Vec are d-dimensional vectors, where you decide what d is, that somehow encode what the words mean. And one of the exciting things that you can do once you have these vectors is you can look at what are the nearest neighbors in this induced d-dimensional space, where you've chosen the dimensionality d. And so, for example, if you want to look at the closest neighbors of the word dog, you get things like cat and dogs, the plural of dog, specific kinds of dogs like dachshund, and puppy, and poodle, and Rottweiler, and so on. What people often do is they take the cosine similarity between two vectors to denote similarity. The nice thing is that if you normalize all your vectors as a pre-processing step so that they're unit length, you can just take the dot product to compare words in this space. So let's say that you want to find all of the words that are similar to dog. So this is actually a product of a matrix W times the vector for dog. So you take all of your words, multiply it by the vector for dog, and then you get similarities for all of the input words. You can take the representation of all of the words in the vocabulary, and so this is just a matrix whose dimension is the size of the vocabulary times whatever dimensionality you chose. You multiply that by the vector that represents dog, which is just a d by 1 vector, and then the matrix that you get out is a 1 by v vector that encodes all of the similarities for all of the words. And because we have fairly fast linear algebra libraries available, this can be done very quickly. You can then take the indices of the k highest values and return that result. And it's really fast. Even for hundreds of thousands of words, this takes on the order of milliseconds. And there's really slick Python packages for loading this information in. You can use GenSim and NumPy to compute this really quickly. And this even works for groups of words. Instead of just a single word, you can do this for each of the words individually and then sum them. But if you do a little bit of algebra, you can first sum the vectors individually, then take the matrix product and look at that result. So hopefully this has given you a sense that working with these dense word vectors can be very efficient, but where do these word vectors come from? And there are a number of ways of computing these word representations, and they're all pretty much the same quality, but there are different choices that are being made. For the sake of concreteness, we're going to focus on just a small subset of the many options that you could take while learning a representation for words. What we're going to focus on is negative sampling. for computing the training objective, and we're going to use skipgrams to represent our context. But once you understand one set of these choices from the menu of options for learning representations, intuitions carry over to the others. One of the things that strikes people as a little bit confusing in Word2Vec is that we're going to represent words with a set of vectors, and we're also going to represent context with a set of vectors, and these are two completely distinct sets of vectors. So there's nothing tying them together, and there's nothing encouraging them to be similar. We're, at the end of the day, going to throw away the context vectors, and that's okay. We're going to initialize both of these vectors with random weights close to 0. So how does Word2Vec work? Like many of the algorithms that we've talked about, it's an iterative algorithm. It's doing something a lot like stochastic gradient descent, taking one example at a time. So let's say that a sentence comes in, and our target word is the word heifer. We want to update the representation for this word. And all the words around it are the context words. We're going to use those representations to update our target word representation for heifer. What we want to do is we want to find vectors W and C1 through 6 such that when we take the dot product of the target word, which again is heifer, with all of the context words around it, and pass it through a nonlinearity, that value is going to be high. At the same time, if we choose some other word instead of heifer, such as comet, we want the same equation, so take the dot product of that corrupted word and the context, pass it through a nonlinearity, we want that value to be low. At the end of the day, we're going to have words so that in the context that they appear in, the dot product between W and C is going to be high. For words that aren't associated with each other, so really bad words that don't make sense in a context, that dot product is going to be low. And then for okay-ish words, they're somewhere in the middle. As a result, words that mean similar things come closer together, and words that don't mean the same thing gets pushed further apart. And then, like I said before, we're now going to throw away the context vector C, and we're just going to use the W vectors. So that's what happens in practice. But to help us understand what's going on inside Word2Vec, let's reconsider what happens with the W vector and the context vector. So consider the product of the W matrix times the context matrix. When you take this product, this corresponds to a matrix where each row corresponds to a word, each column corresponds to a context, and then each cell has the association between a word and context. So at this point, this should remind you of something. This looks a lot like if you took the word context matrix and ran an SVD on it. Both of these matrices are really skinny compared to the underlying dimensionality of the data, and if you just throw in a small d by d matrix S in the middle of it, this looks exactly like an SVD on your data. And you can show that Word2Vec is doing a similar decomposition of the data. And with a few tricks, you can get SVD to work almost as well as Word2Vec. So why are we using Word2Vec? The simple truth of it is that it's really fast compared to an SVD, and because it's online, you can just throw additional data at it very easily. It also scales if you have, say, a cluster of computers, you can distribute the computations very easily. What we're now going to talk about next is go a little bit deeper into the math for how you actually update the parameters for learning Word2Vec representations. And although Word2Vec itself isn't deep learning, these representations will be very useful to us when we move on to things like RNNs and LSTMs that need learned representations to do their job effectively. And so those are deep learning algorithms that build on the representations learned by these shallow algorithms.